9.2 Analysis Model. Isolated System. Momentum. The outline of this video is as follows. We will explore the isolated system model for momentum and the principle of conservation of total momentum. We will discuss how to identify isolated systems and prevent common pitfalls. Finally, we will apply this model to two examples: the recoil of an archer and the kinetic energy of the Earth. Let us define the isolated system model for momentum. For a system of two interacting particles, if the time derivative of the total momentum is zero, the momentum is conserved. This implies that the total momentum of the isolated system must remain constant over time. Mathematically, the change in total momentum, delta P total, is zero. An isolated system is defined as one on which no external forces act. All forces involved must be internal to the system. We can now state the principle of conservation of momentum. For a two-particle isolated system, the initial total momentum is equal to the final total momentums. This is a vector equation, which means the total momentum is conserved independently in each direction, x, y, and z. A fundamental principle is that whenever particles in an isolated system interact, the total momentum of that system does not change. Here is a summary of the analysis model. If you identify a system that has no external forces acting on it, it is an isolated system, and its total momentum is conserved. Common examples include a cue ball striking another ball, or a spacecraft firing its rockets. A key pitfall to avoid is assuming that the momentum of a single particle is conserved. Remember, it is the total momentum of the system that remains constant, not necessarily the momentum of individual components. This slide presents example 9.1, the archer. We have a 60-kilogram archer standing at rest on frictionless ice, who fires a 0.030 kilogram arrow horizontally at 85 meters per second. We want to find the velocity with which the archer moves across the ice after firing. We categorize the system as the archer plus the arrow. Since there are no external forces in the horizontal direction, we can apply the isolated system model. We will now solve for the archer's velocity. Let the archer be particle 1 and the arrow be particle 2. Before the arrow is fired, the system is at rest, so the total initial momentum is zero. By conservation of momentum, the final momentum must also be zero. We write the equation: mass 1 times velocity 1 final plus mass 2 times velocity 2 final equals 0. Rearranging this allows us to solve for the archer's final velocity. Now consider a what-if scenario. What if the arrow were fired at an angle theta with the horizontal? The magnitude of the archer's recoil velocity would decrease. This is because conservation of momentum applies to the components. We only use the horizontal component of the arrow's velocity. The equation becomes mass 1 times velocity 1 final plus mass 2 times velocity 2 final times cosine theta equals 0. If the arrow is fired straight up, cosine theta is 0 and there is no horizontal recoil. In example 9.2, we verify the claim that we can ignore the Earth's kinetic energy when a ball is dropped. We define the system as the ball plus the Earth, which we treat as isolated. We apply conservation of momentum. Since the initial momentum is zero, the final momentum of the ball and the Earth must sum to zero. This relationship allows us to find the ratio of the Earth's speed to the ball's speed, which is the inverse ratio of their masses. We continue by setting up the ratio of the kinetic energies. Using the velocity relationship we just derived, we find that the ratio of the Earth's kinetic energy to the ball's kinetic energy simplifies to the mass of the ball divided by the mass of the Earth. Substituting order of magnitude values, with the ball at 1 kilogram and the Earth at 10 to the power of 25 kilograms, we get a ratio of 10 to the power of negative 25. This extremely small fraction justifies ignoring the Earth's kinetic energy. To summarize, an isolated system is one with no net external force. In such a system, the total momentum is conserved, meaning the change in total momentum is zero. This implies the initial total momentum equals the final total momentum. This fundamental principle holds true for interactions like collisions and recoils, regardless of whether the internal forces are conservative or non-conservative. Finally, here are some review questions to test your understanding. In the Archer example, the system starts with zero kinetic energy but ends with positive kinetic energy. Ask yourself if energy is conserved and where that energy comes from. Also, consider a collision between a large truck and a small car. Determine which vehicle exerts the greater force and which experiences the greater change in momentum.